Hello, everybody, and welcome to the sixth meeting of the beer evaluation course. This time, we will discuss yeast and fermentation. Just wanted to remind you that if you like the video, please hit the like button, and if you have any questions, please comment on the video and I will answer. If you haven't subscribed to my YouTube channel, please click on the subscribe button and click the bell icon to get notified when my next videos come out. In addition, if you haven't followed me on my social media, you can see them changing on the screen right now or find them in the description below. And now, without further ado, let's get to our presentation of the day about yeast and fermentation. This is the sixth presentation of the beer evaluation course about yeast and fermentation. This is the layout of today's presentation. We will discuss by talking about the history of using yeast, the basics of good fermentation, fermentation biology and esters, choosing the right strain, fermentation timeline, yeast nutrition, aeration, fermentation temperatures, and the fermentation endgame. And we will start by talking about fermentation history. Throughout history, mankind believed that fermentation is part of the divine mystery. Around the 12th century, brewers began transferring yeast between batches, thus domesticating the yeast. But that doesn't mean that they knew that they were yeast. To prove that, the beer purity law enacted in Germany in 1516, the Reinheitsgebot, does not mention yeast as one of the ingredients from which beer is made. Towards the end of the 17th century, Anton van Leeuwenhoek saw through a microscope that yeast are made up of many small particles that are connected to each other. In 1789, Antoine Laurent Lavoisier first described the fermentation process as a process in which sugar is turned into alcohol and CO2, but he still thought that it was a chemical reaction rather than a biological process carried out by living organisms. Only about 80 years later, Louis Pasteur proved that yeast are living things and that the fermentation process is a biological process. Louis Pasteur published his findings in 1879, thus creating a new field of research called biochemistry. But Louis Pasteur didn't stop there. He went on to prove that yeast are indeed responsible for fermentation, but that yeast and wild yeast are also responsible for off flavors. All this laid the foundations for Emil Christian Hansen from Carlsberg Labs in Denmark to isolate the first lager variety and used it to make beer on November 1883. But they didn't realize that they discovered a new species of yeast until 1908. The beer that was created changed the beer world in that it was very clean and was kept for a long time without spoiling. Having personally led a sensory evaluation panel of beers with cultures from the time of the Egyptian Empire in Israel, from the Bronze Age, I believe that we owe the popularity of beer nowadays to Emil Christian Hansen and his team in Carlsberg Labs. After talking briefly about the history of fermentation and the fermentation biochemistry, we will move on to talk about what are the conditions for a good fermentation. For good fermentation, we need to pay attention to 7 things. We need the right sugars, healthy yeast, enough oxygen, enough nutrients that the yeast needs, a suitable fermentation system with temperature control, and constant monitoring of the fermentation. And now we'll move on to talk about each of these conditions and how they can affect the final beer. We'll start by talking about the sugar. There are all kinds of sugars, and each, depending on their complexity, has different fermentation conditions. For example, yeast will not start digesting dextrose until they've finished digesting all the glucose. In addition, The type of sugar also affects the flavors of fermentation. For example, fermentation of wort with more glucose will create a more estery beer than wort with more dextrose. In addition, the sugar source can vary. Indeed, the majority comes from barley, but sugar can also come from different starchy grains such as rice, corn, wheat, oats, rye, and others. The sugar source can affect the nutrients available for the yeast and as a result affect the flavor. Next are the yeast themselves. As we saw previously, yeast turns sugar into alcohol, carbon dioxide, and other compounds. The yeast doesn't do it because we want them to make alcohol. They do it because they need energy and other materials to reproduce. Yeast don't really care that we want beer without any off flavors. When we choose a yeast strain, the main thing to consider is what are the flavors and aroma that fits the style of the beer we want to make, and does the strain produces these flavors. Of course, we will use healthy yeast and the suitable amount for optimal fermentation. The third factor is oxygen. Why is oxygen needed? After all, in the previous presentations, we talked negatively about the presence of oxygen in the beer or the wort. The only time in the brewing process where oxygen is positive and should be added to the wort is after the wort is already cold right before fermentation. Oxygen at this point is critical to the growth and health of the yeast. The yeast need oxygen to create sterols used to build cell membranes for newly created cells. Therefore, at the beginning of each fermentation, we add oxygen and ventilate the wort. Oxygen levels of 8 to 10 ppm should suffice, but levels vary between strains and other factors such as gravity and nutrient requirements of the yeast strain. I will cover this later in the presentation. Next, we need to discuss yeast nutrients. When we talk about nutrients, we talk about vitamins and minerals that are needed by the yeast to grow, metabolize sugars, and finish the fermentation well. In most cases, a wort that is made entirely from grains, that is, without sugar additions, will contain enough nitrogen, minerals, and vitamins for a healthy fermentation. Yeast take up minerals and vitamins from the environment to produce proteins required for growth and fermentation. Therefore, it is very important, but it is also easy to make sure that the yeast have sufficient nutrients. I will expand on this later. It turns out that the fermentation system, meaning the fermenters, also affect the fermentation. Traditionally, large and open pools were used to ferment, when today we use closed system that can be cleaned and sanitized. But it is important to note that the shape and geometry of the tank can also affect the outcome of the fermentation. As a rule of thumb, the higher the pressure is on the yeast, they will produce less esters. Therefore, in beers where we want to have esters, such as German wheat beers and English barley wine, we will use fermenters with as little pressure as possible, meaning in shallow, wide open pools. Conversely, if we want beers without esters, we will use high and narrow fermenters that will create pressure on the yeast from the weight of the fluid. Or, if we desire higher pressure, use a closed tank to retain the emitted CO2. After the shape of the fermenter, we will talk about temperature control. A relatively constant and closely monitored temperature is necessary for consistent and high quality beer. In most cases, when there is a problem with the beer, and it is not a sanitation problem, the first place to check will be temperature control. Temperatures that are too high or too low greatly affect the production of many off flavors and the ability of the yeast to clean them. Where there are large and uncontrolled temperature changes, we will get a beer with more off flavors. The smaller the batch, for example, in homebrewing, the more it will be affected by changes in the temperature. The last thing we will talk about is monitoring the fermentation. Equipment for monitoring fermentation can range in a wide price range, and also how complicated it is to operate. If it's a huge brewery that has its own lab and people in charge of doing tests, then everything is fine. But even a homebrewer who works alone can learn a lot by observing a thermometer and some manual tests. The most important things to measure and monitor are temperature, gravity at any given moment, pH, oxygen, and carbon dioxide. The good thing is that today there are all kinds of devices like the tilt and ice bundle that float in the beer during fermentation and measure gravity and temperature every 15 minutes and transmit to the network for logging. So you can take lots of measurements and get a graph like we see on the right. These logs are very useful if there is a problem with the beer, and if we compare them to previous batches, they can point to the source of the problem. The other three are more complicated to measure continuously at the home level at this time. Now that we've talked about what we need for a good fermentation, we'll move on to talking a little bit about fermentation biology, esters, and other compounds that are produced by the yeast. Let's start by talking about what are yeast. Yeast are single-celled organisms from the fungi kingdom. An average yeast cell will be 5 to 10 microns in size and round or elliptical in shape. There are more than 500 known species of yeast. Note, not varieties, species. As brewers or judges of beer, wine, mead, cider, and distilled beverages, we're interested in two main strains, Saccharomyces cerevisiae, which are ale yeast, and Saccharomyces pastorianus, which are lager yeast. An average yeast species has just over 6,000 genes on 16 chromosomes. Indeed, if you compare it to the 36,000 genes in human, it is not much, but we still don't understand how only 6,000 work. Brewers or bakers' yeast have, over the years, lost the ability to mate with other yeast, which means that they reproduce only by mitosis and not by gene exchange. This is the outcome of the selection of the brewers who move them from fermenter to fermenter. The plus of the trait is that we have much more consistent results in fermentation because the genetic load of the yeast remains the same. If we take a yeast cell and look at it under a microscope, we can see small organelles inside the cell. The important organelles of the cell are the cell membrane. This is the envelope that isolates the contents of the cell from its environment and has the ability to determine which substances will move in and out of the cell. The plasma membrane that surrounds the internal cell contents. The cytoplasm, the substance that is inside the cell and includes water, proteins, nutrients, and more. The mitochondria, which is an ancient bacterium that is responsible for creating energy in the presence of oxygen. And vesicles, which are mechanisms for transferring substances within the cell. The nucleus, where the genetic material is stored, and the endoplasmic reticulum, which is responsible for transporting proteins inside the cell. Of course, there are other organelles in the cell, but they are less important to us as brewers. What does a yeast cell do during its life? It eats and grows. When we talk about growth of yeast, we do not mean that a specific cell becomes larger, but about the creation of new cells. When we pitch yeast into the wort, the first thing that they will do is to use their glycogen reserves and the oxygen that is around. They then begin to metabolize the sugars in their environment in order from the simplest sugars to the more complicated ones. So basically, what determines the metabolism, the attenuation, and the rate of fermentation of the yeast are the ability to metabolize different types of sugars, the proportions of the different sugars in the wort, and the amount of nutrients in the wort. Why do we care about yeast metabolism? Because one of its byproducts, alcohol, is very important to us as brewers. So, how is alcohol made by the yeast? The process can be divided into two main parts. The first is actually the breaking of the glucose molecule into two pyruvate molecules and always happens. The second step, on the other hand, only happens in cases where there is no oxygen and is the conversion of pyruvate into alcohol. If there is oxygen, the yeast will be able to extract much more energy from the sugar and then turn it into carbon dioxide and water. If we look at the diagram on the right, we see that glucose is broken down into pyruvate by a process called glycolysis. And after that, pyruvate turns into acetaldehyde and from there into ethanol. This process of converting pyruvate into alcohol is reversible in the presence of oxygen, and the alcohol can revert to acetaldehyde and pyruvate. Another aspect that is important to note about the yeast is their ability to stick to each other and sink. This ability is called flocculation. Different strains of yeast have different flocculation ability, so it is important to choose a strain that matches the style, not only in terms of flavors, but also in terms of flocculation. If we want to make most of the styles, we will need a strain with good flocculation in order to clarify the beer easily. If we want to make a hazy style, whether it's hazy IPA or German wheat beers, we need to use a strain with less flocculation. In most cases, the varieties are classified into three classes according to their flocculation. High flocculation sediments quickly, sometimes even before they finish cleaning the beer from off flavors. Therefore, the beer will have higher than normal levels of diacetyl and lower attenuation. You can see an example of those on the right in the right picture marked with B. Medium flocculation usually produces clean and balanced beers, and low flocculation, in which the yeast hardly stick to each other and will remain in the liquid. It is good for German wheat beers and hazy IPAs, as I said before. These will, in most cases, leave a haze and a yeasty taste and aroma. You can see an example in the picture marked with A. Now we'll move on to talk about flavoring substances that the yeast produce, and we'll start with esters. Esters are volatile compounds formed from the interaction of an organic acid and an alcohol. Examples of common esters include ethyl acetate, which is composed of ethyl alcohol and ethanol, and acetic acid. This substance has a red apple aroma in small amounts and a burning solvent aroma in large amounts. There is also ethyl caproate, which consists of ethyl alcohol and caproic acid and has an apple aroma as well. Isoamyl acetate, which is composed of isoamyl alcohol and acetic acid, has the aroma of banana in small amounts or bubblegum in larger amounts. The formation of esters depends very much on the yeast strain and the fermentation conditions. As a rule of thumb, the higher the temperature, especially at the beginning of the fermentation, the more esters we will get in the beer. In addition, the more pressure there is on the wort, the less esters we will get in the beer. Please note, the most common acid in a yeast cell is acetyl-CoA, and the most common alcohol is ethanol. Therefore, ethyl acetate is very easily formed in any beer. In order to avoid the creation of ethyl acetate, you should start the fermentation 2 degrees less than the temperature of the rest of the fermentation. The following flavor compounds are the so-called fusel alcohols. These alcohols taste like ethanol, but they can also add a sensation of heat, alcoholic burn, and solvent to the beer. These compounds are not desirable in all styles of beer, and we want to avoid them. Some examples of such alcohols are N-propanol, isoamyl alcohol, and isobutanol. The yeast can create such alcohols during the lag phase. Conditions that cause the yeast to develop quickly at this stage, such as high temperature, aeration, and nitrogen, produce more such alcohols. Therefore, once again, it is recommended in the first stage of fermentation to put it at 2 degrees less than the main fermentation. The next group of substances that yeast can produce are phenols. Phenols can reach beer from raw materials, and in the previous lecture we saw that they can come from the hops, but they can also form as the result of the fermentation. These compounds have a wide range of flavors and aromas. They can smell like cloves and other spices or smoke at a desired range, but can also add unwanted flavors of plaster, burnt plastic, burnt tire, smoke, and more. Compared to fusel alcohols, phenols will not break down by aging and will remain in the beer even after a very long time. All beer styles consider phenols as unwanted, with the exception of cloves in German wheat beers and black pepper in Belgian beers. Most of the yeast that brewers use have lost the ability to produce phenols with the exception of wheat beer yeast or Belgian style yeast. The next compound we will talk about is diacetyl. Diacetyl belongs to a group of substances called vicinal diketones or VDKs, together with another substance called 2,3-pentonedione, which gives beer a flavor of honey. This group of substances can oxidize in the bottle and give the beer aromas of butter and honey. What happens is that an acid called acetolactate comes out of the cells during the lag phase and the exponential phase, and when it oxidizes, it becomes diacetyl. At the end of fermentation, the yeast will absorb the diacetyl and convert it into a flavorless and odorless compound. The last group of substances we will talk about are sulfur compounds. Yeast produce sulfur compounds during fermentation. These compounds are so volatile that a healthy and strong fermentation will blow them out of the beer with the emitted carbon dioxide. Therefore, with a lager fermentation, which is done at lower temperatures and correspondingly at a lower rate, we will get more sulfur left in the beer than in fermentations with an ale yeast. Sulfuric compounds can be DMSO, which is an oxidized version of DMS and has no aroma or taste. But the yeast can scavenge that oxygen and turn it into DMS, or SO2, which can give an aroma of burnt match, or even SH2, which will give an aroma of boiled eggs. The key to avoiding such compounds in beer is to maintain a good, healthy fermentation that will vent these substances out. Now that we've talked about fermentation and the flavor that yeast can produce, we'll move on to talking about how we choose a yeast strain for the beer we want to make. What are the parameters according to which yeast are selected for a beer? The first parameter is attenuation. When we say attenuation, we mean how much of the sugar in the wort the yeast will metabolize into alcohol and carbon dioxide. If the beer is dry and hoppy, a variety with a higher attenuation will be chosen. If it is a sweet and malty beer, a variety with lower attenuation will be chosen. The second parameter we will consider is the flavor profile of the yeast. Do we want a variety that will not give fermentation flavors? We call this clean fermentation or a clean yeast strain. Or alternatively, maybe we're making a Belgian beer and we want there to be phenols, or an English beer where we would like to have some esters. We will of course also consider the flocculation of the yeast. As we said, we will choose a strain with a low flocculation if it's a beer with haze, or a strain with high flocculation if it's a sweet malty beer. If we are a commercial brewery, we will also look at the availability of these yeast to make sure that we don't get stuck and suddenly not be able to make a certain beer. And the last thing to consider is the optimal working temperature of the yeast. For example, if we do not have temperature control, we will want to use the yeast that works the best at the temperatures available to us. Yes, it is absolutely possible that there is not one strain that will meet all of the criteria, and we may have to use several strains together. I recommend for homebrewers to experiment with different strains, different temperatures, oxygen levels, and more to understand how each of these parameters can change the result. In a 1997 article, George Fix divided brewer's yeast strains into 7 categories. Ale has 5 categories. The first are clean strains. In this category, you can find the American, Scottish, and European strains. There are also fruity strains, among which you can find the British, Irish, Australian strains, and some of the Belgian strains. There are the hybrid strains of alt beer and Kolsch, which ferment at much lower temperatures than other ale yeast. There are phenolic yeast, such as German wheat beer yeast, some Belgian ales, and Trappist ales. And there are the eccentric varieties of wheat beer, Chimay, and more. In lager yeast, there are two main categories. In lager yeast, there are two main categories. The first group is the dry lagers, like American lagers, German pils, and Czech lagers. And the second group is full lagers, such as Munich Helles, Dunkel, Schwarzbier, Doppelbock, and more. 2 slides ago, I said that sometimes there will be no escape but to use different types of yeast. Let's expand on that for a moment. Really, the vast majority of beers are made with one strain of yeast, but more is also possible. Why would we want to use more than one yeast strain? Some examples of that could be to dry a beer that is too sweet by adding neutral yeast with higher attenuation. You can mix strains with different flavors that complement each other, or to create a special flavor profile. It is also important to note that yeast creates most of the flavors in the first 72 hours of fermentation. Therefore, if we want the yeast to add flavor, we need to add it in the beginning. Another species of yeast that needs to be expanded on is Brettanomyces, or Brett for short. It's actually a different species of yeast. Like brewer's yeast, Brett can arrive on dust, insects, and other things that can contaminate the beer. But, of course, there are also beers that have Brett in them on purpose. For example, Brett is responsible for a large part of the flavor profile of lambic beers, and its strains such as Brett bruxellensis, Lambicus, and Anomalus are found in these beers. Brett, compared to brewer's yeast, is special in that it can convert sugar to acetic acid and ethanol in the presence of oxygen, and it can also digest other types of yeast. So, even if the fermentation is done, Brett can continue to ferment the beer in the bottle and increase the pressure. Brett's common flavors are horse blanket, ranch, sweaty horse, wet dog, band-aid, leather, wet wool, digestive acids, burnt beans, burnt plastic, black pepper, cage of rodents, and other such pleasant descriptions. The problem is that Brett needs a very small population of several cells to develop and give noticeable aromas and off flavors. Another important species of yeast to talk about is Saccharomyces diastaticus. Saccharomyces diastaticus is a subspecies of Saccharomyces cerevisiae. The problem is that these strains can metabolize complex sugars, dextrins, and even starch. These yeast include almost all the Belgian strains and also the strains of the Belgian wheat beers. The problem with them is that even if there are few cells, they will metabolize the dextrins little by little, and over time, we will get higher and higher carbonation until the bottles explode. Therefore, breweries that make wheat beers or Belgian beers use these yeast in the main fermentation to give flavor to the beer. Then, a sanitary filter is used to remove all the cells from the beer, and then the wort is put into bottles with other yeast to carbonate. Because it takes very few cells to start such an infection, you should think 10 times before introducing such a strain into the brewery. Don't bother with Belgian beers or wheat beers unless you intend to switch to only these styles, or you have the equipment and the ability to disinfect the equipment and to check that there is no such contamination. It's just not worth it. If you have already decided to go for it, then it is advisable not to bottle the beer with these strains. And if it is already bottled, drink it quickly. Within 3 weeks to a month, problems will become noticeable. After we talked about how to choose a yeast strain and from which species it's better to avoid, we will move on to talk about the fermentation timeline. We divide the fermentation process into 3 main phases. The first phase is called the lag phase. This phase lasts between pitching the yeast and up to 15 hours into the fermentation. At this phase, the yeast begins to acclimate to the new environment. The cells begin to use oxygen, minerals, and amino acids from the wort. A wort made with 100% malt has almost everything the yeast needs for a good fermentation except oxygen. Besides, if we don't want to have enough yeast, for example, in beers with a high alcohol content, we can put a slightly higher temperature at this phase to make up for it. But beware, it can cause the appearance of esters and fusel alcohols. The second phase is the exponential phase. It will start from the end of the lag phase, which can happen after 4 hours or up to 15 hours, and will end after about 4 days. At this phase, the yeast quickly consume the sugar and produce ethanol and carbon dioxide. Ale yeast creates a layer of foam on the beer, and this layer can rise high in the fermenter. So, as a rule of thumb, we will make sure that there is at least 20% headspace in the fermentation tank. The yeast consumes the sugars in the wort in a specific order from the simplest, such as glucose, fructose, and sucrose at first. These will be about 14% of the sugars in an average wort. And then the yeast will metabolize the maltose, which will be about 59% of the wort, and then the maltotriose. When the yeast are at this phase and we see their activity, we call it high Kreuzen. The third and final phase is called the stationary phase. At this phase, the yeast has already consumed most of the sugar and their growth begins to slow down. At this phase, the yeast has already produced most of the flavors and aromas and they move on to clean the beer. When the beer matures, the yeast clean the diacetyl and the acetaldehyde into aromaless and tasteless compounds, and sulfur is also expelled out as a gas. At this phase, the yeast also undergoes flocculation and sink. At the end of this stage, we cool the beer down to 2 to 4 degrees to stop the biological activity and allow the beer to mature. Now that we've talked about the fermentation timeline, we will move on to talk about the nutrients the yeast needs. Like all organisms, yeast needs an orderly supply of sugar, nitrogen, vitamin, phosphorus, and minerals to live and develop. The exact needs vary from species to species. A wort made with 100% malt will have everything the yeast needs except oxygen and zinc. The yeast also needs a lot of amino acids in the form of nitrogen. A good source of nitrogen is the ammonium phosphate or DAP. And finally, the minerals that yeast needs are calcium, potassium, magnesium, zinc, and other metals. Brewers will usually add yeast nutrients in the form of DAP or cervomyces towards the end of the boil. The next thing the yeast need is oxygen, so we will move on to talk about aeration of the wort. When the wort is cold and in the fermenter, the brewer will add oxygen or filtered air to the wort. If there is not enough dissolved oxygen in the wort, we risk stuck fermentation, long fermentation times, beers that have not reached the expected attenuation, stress to the yeast, and off flavors. The brewer can add filtered air, or oxygen. Common methods of doing this are shaking the fermenter, using a stirrer that attaches to a drill, and a carbonation stone. So, why do we need oxygen in the wort at the beginning of fermentation? When the yeast reproduce, among other things, they have to prepare membranes for the new cells. To synthesize membranes, the yeast has to produce substances called sterols and unsaturated fatty acids. To make these sterols, the yeast use oxygen to convert acetyl-CoA into sterols and fatty acids. Since the yeast needs to produce fatty acids, many experiments were done with adding different oils, such as olive oil, at the beginning of the fermentation to compensate for the lack of oxygen. It does not work well because the yeast manages its metabolism carefully and does not create too many sterols and fatty acids. After we understand why we need oxygen at the beginning of fermentation, we need to talk about how much oxygen is needed. In a wort with an average gravity and an average amount of yeast, you need 8 to 10 ppm of oxygen for good and healthy fermentation. The higher the gravity, the more yeast and oxygen is needed. It is important to understand that if air is used, in the best case, we will get 8 ppm of dissolved oxygen in the wort. To reach higher levels, you will need to use pure oxygen. You can see in the small table here how many ppm of dissolved oxygen we will get with shaking for 5 minutes or with the flow of oxygen for certain times to the wort. You can clearly see the difference in efficiency. After we talked about oxygen and its importance at the beginning of fermentation, we need to talk about fermentation temperatures and their importance. Let's start by talking about heat. When yeast metabolize sugar, heat is generated from these reactions. This heat can raise the temperature of the wort, and if it is not controlled, the yeast can die, create off flavors, and or undergo mutations that can also cause off flavors. Yeast grows faster at higher temperatures, but brewers actually prefer temperatures as low as possible, where the yeast still work. This way, the yeast will produce as few off flavors as possible. Yeast are unicellular organisms. Therefore, very small changes in the ambient temperature is a big deal to them. If the temperature rises, their metabolic rate increases, and they also begin to produce proteins designed to stabilize activity during the heat shock state. According to studies, yeast react to different forms of stress in a similar way and with the same proteins. Therefore, we will get similar off flavors if we have a heat shock, lack of nutrients, or lack of yeast at the beginning of the fermentation. If the temperatures are too low, we will get a slow and very long fermentation. If the temperatures are higher, we can get up to a tenfold increase in acetaldehyde and 1.5 times more of ethyl acetate, which can become solventy. Finally, after we've talked about why the yeast needs a constant temperature, we need to talk about which temperature the yeast needs, or how to plan the fermentation timeline in terms of temperatures. Like I said, the yeast needs a constant temperature during fermentation. If we have an optimal amount of cells and nutrients, a good fermentation profile for most ale fermentations would be to start with a temperature 1 to 2 degrees below the main fermentation temperature. The reason for this is that we want to slow down the activity of the yeast during the lag phase so that as few off flavors are formed as possible. Then raise the temperature to the main fermentation temperature of the yeast during 18 to 36 hours. So we actually increase by 2 degrees in 36 hours. It's a very slow increase. After that, we will maintain this temperature until 66 to 75% of the sugars have been metabolized. At this point, we will raise the temperature by 2 to 5 degrees for 24 to 48 hours. If we do this, the yeast will work faster in the phase of cleaning the beer from off flavors and will clean as much of them as possible before settling. In the final stage, we lower the temperature to -1 to 5 degrees centigrade. This temperature will stop the biological activity and the yeast will settle. This will also help the beer clarify before packaging. Now that we've talked about all the things that yeast needs during fermentation, we'll move on to talk about what happens at the end of fermentation. Let's start by talking about attenuation. We said that attenuation is the percentage of the sugars in the wort the yeast has metabolized. To calculate attenuation, brewers measure the gravity at the beginning of fermentation and at the end of fermentation. The attenuation is calculated as the ratio between the difference between the measurements divided by the initial gravity minus 1. Then, multiply by 100 to convert the result to percentage. It is very important to follow gravity and attenuation. There are devices like the Eisspindel, the tilt, or the wrapped pill that measure gravity continuously and report to some logging server. This data can be used by the brewer to learn about the fermentation of a certain beer and the sugar composition of the wort. By the way, the normal attenuation is specified in the strain spec sheet. You can find this data in the manufacturer's website in most cases. If we got a lower attenuation than normal, this could indicate a problem that the beer will be too sweet. The problem can arise either from the composition of the sugars in the wort or from problems of lack of nutrients, oxygen, or irregular temperatures. The next topic to talk about at the end of fermentation is flocculation. Brewers in most cases choose the strain of the yeast that they will use mainly based on its flavor and aroma. This means that brewers will also have to deal with strains with different flocculation. As a rule of thumb, colder conditions at the end of fermentation will encourage flocculation and sedimentation, resulting in a clearer beer. Brewers can add fining agents that promote flocculation at this stage. You can add gelatin if you do it at home, or isinglass or polyclar if it's on a commercial scale. A beer that seems clear to the human eye will contain less than 100,000 cells per milliliter. We will talk in detail about the subject of clarification in the next presentation. Now, let's discuss diacetyl and cleaning the beer from off flavors at the end of fermentation. We said that as the yeast grow, they create acetolactate that can oxidize and become diacetyl. During the stationary phase, the yeast absorb the diacetyl and turn it into a tasteless substance. To lower the levels of diacetyl in the final beer, you can do 3 things. The first is to keep the wort at a degree or 2 less in the lag phase to suppress the formation of acetolactate, and a degree or 2 more in the stationary phase to encourage the cleaning of the diacetyl from the beer. The second is to avoid separating the beer from the yeast before they've had time to clean the beer from off flavors. And the third is to avoid oxidation during the packaging stage. Oxygen can restore the diacetyl and also turn alcohol back into acetaldehyde. The last topic we will talk about today is lagering. Lagering means to keep the beer at low temperatures after fermentation. The legendary beer scientist from Belgium, Jean de Klerk, defined 6 goals for lagering in 1957. The first is to allow for better clarification of the beer. The second is to carbonate the beer with the help of external carbon dioxide or a second fermentation. The third, to improve the flavor of the beer. The fourth is to cause chill haze to sink. And the fifth is to avoid oxygen found in the beer because the yeast will use it and clean it as well. The lagering process can be between a few days in modern times or up to a few months, depending on the strength of the beer. It is mainly done in beers fermented with lager yeast. This is where we finish the sixth presentation of the beer evaluation course about yeast and fermentation. I hope that the talk was informative and interesting, and I want to remind you that if you like the video, please hit the subscribe button, like button, and click on the bell icon to get notified when the next videos come out. If you have questions, please write them in the comments. I promise to go over them. In addition, you can see my social media handles change on the screen right now or find them in the description of the video. You're welcome to follow me to know when my next projects come out. Thank you for listening. I was Omer Basha, and see you in the next presentation where we will discuss advanced topics in brewing.